Hello, everybody, and welcome to Chapter 3. We're going to be looking at ionic and covalent compounds in this chapter. Now, if you remember how we started last chapter, we had this same slide, right? We know that in chemistry, matter is composed of elements and compounds, and we defined these before. So see if you remember. Here are some examples of elements, some examples of compounds. And we said that an element is a substance composed of only one type of atom that cannot be broken down. A compound is a substance composed of two or more different atoms held together by chemical bonds, and it can be broken down back into its elements. I wanted to point out only one type of atom can include things like oxygen, which is actually O2, so it's two oxygen atoms with a bond between them, and its elemental oxygen shows up that way. Only one type of atom. But our compounds are different types of atoms. So this was last chapter, and compounds this chapter. So we'll be looking at two different types of compounds generally, ionic and covalent. So atoms in a compound are held together by a chemical bond, right? And a chemical bond results from the interaction between valence electrons in the two atoms involved in the bond. And there are different types of valence electron interactions. And we define the compounds by these types of electronic interactions. So the first is ionic. An ionic compound is one in which the valence electrons, which remember are the highest energy, outermost, highest n level electrons, if valence electrons transfer from one atom to another, these are called ionic. We're going to focus on these in the first two sections. And covalent is when the valence electrons are shared between atoms, right? Covalent. Co is sharing. And this will be the last two sections. So we talked about elements, the periodic table, and all that last chapter. And we talked about how some electron configurations can be more stable, things like that. So why do compounds even form at all? Right? Why don't we just have elements and atoms around? Well, thank God they do. So why do compounds form? Well, like like most things in physics and chemistry, they form because they lower potential energy, right? It's more stable. Like think about a ball on a hill, and it's going to roll down to lower potential energy. And you can draw a similar kind of diagram of, let's say, two atoms separated out up here. And if they come down together and form a compound, it's going to be lower in potential energy than the separate atoms that form them. And atoms form compounds to attain filled valence energy levels. So a filled valence energy level is lower potential and more stable. Noble gases, then, the ones all the way off to the right of the periodic table, they already have a filled valence energy level. So they actually don't form chemical bonds, right? They're noble. They don't interact with all the others. The core concept here is that by forming compounds, atoms achieve filled valence energy levels, and filled valence energy levels is a more stable arrangement of electrons. And it's more stable than the isolated atoms in their elemental forms. Okay, so that's kind of an introduction, just compounds in general. The first section is about ionic compounds, right? So remember, this is when at a transfer of electrons. And we're first going to look at monatomic ions. So an ionic compound is composed of oppositely charged ions held together by ionic bonds. So you're going to see this word a lot, even down here. Oop, there it is again. So the simplest ionic compounds contain monatomic ions. What that means is the components of it are simply formed when a metal transfers a electron or a couple electrons to a non-metal atom. And so mon means one, so one atom. So it's just from one atom to another. That's it. And then they're called cations if it's the metal. So the metal cation, and the non-metal is called the anion. And yes, that is cat ion, not anything else. Um, so when the metal loses the electron to the non-metal, what's left over is a positive charge, and that's called a cation. And when the non-metal takes on the new electron, it now has an extra electron relative to protons, and so it has a negative charge. And they're held together by electrostatic attractions, right? Opposite charge, opposite signs attract. So once the electron transfers, now they're attracted to each other. Here's an example of sodium chloride. So on the left, we see the neutral atoms. Sodium right here, Na, right? That's, if you look on the periodic table, find it. You might want to go ahead and pause, find it on the periodic table. Okay, here's a clue. It's got 11 protons, so it's element number 11. And it's on the left. It's a metal. It's in group 1A. It's an alkali earth metal. Sorry, just alkali metal. Okay. And chloride, or chlorine, it's in group 7A. It's called a halogen. And it's a nonmetal. And for reasons that we will talk about eventually, the electron will lose, the metal will lose the electron, and the nonmetal will gain the electron. So that's the transfer. Now what's left over here is sodium, the plus, and chlorine with an extra electron and a minus. And then they will form themselves into a lattice structure like so, where there is a 1-to-1 ratio of chlorine minus and Na plus ions. So this is on the small atomic scale, just a drawing, but this is actually salt, right? This is sodium chloride is table salt, and so it makes these nice crystals that you would see under a microscope if you looked at salt. And then atomically, it's just alternating cations and anions. So here's some of this all again. Ionic compounds are held together by strong attraction of opposite charges. They importantly have a net charge equal to 0, right? Compounds are neutral. All compounds are neutral. So they have a net charge, meaning the pluses and the minus of the compound cancel out. And so this helps us to determine the ratio of cations to anions. When a cation, positive charge, and an anion, negative charge, have charges of the same magnitude, the ratio of the cation to anion is 1-to-1, like sodium chloride. For every Na plus, there's one Cl minus. So this ratio would be reflected when we write the formula unit. So the formula unit here would just be NaCl. But it's not always a 1-to-1 ratio, but it is always neutral. Okay, and so we may actually end up with some subscripts here in these spots. If it's 1, it's assumed to be 1, and we don't put it there. So the cations and anions themselves result from the transfer of electrons, right? You go from neutral to charged, and then we just have special names for whether it's plus or minus. Since it has a charge, we also know it has an unequal number of protons and electrons. And here's an equation that we came up with last time on the POGL, that the charge is equal to the number of protons minus the number of electrons, right? And the charge is given as a superscript onto the right. Superscript means up, right? So Na plus, Cl minus, Mg 2 plus, oxygen O 2 minus, right? Okay, I think we'll end part one here and we'll come back and work on answering these questions.